what is that tied to?
Well, it's because they are closer to the sun,
Okay.
so whenever we're looking at them, we have to be looking towards the sun.
Right, so good. So basically you'd expect to see them when? What time of day? Well, yeah, you could see them in day or night if you have a telescope. About what time?
Sunset or sunrise.
Sunrise or sunset, that's right. So sunrise, sunset. That's especially true for Mercury. Venus, of course, can get pretty high in the sky. But you'll never see Venus high in the sky at midnight. What planets will you see high in the sky at midnight? Different planets. The superior planets. So these can get into opposition. Okay, so they're directly opposite the sun from the Earth. What else characterizes the motion of superior planets? We didn't really talk about it, maybe you've read it.
They experience periods of retrograde motion.
Retrograde, okay, retrograde. Basically, all the planets follow the ecliptic, roughly speaking, at night after night, progressing west to east, just like the moon will, just like the sun will. Not every night they go from east to west, but if you watch the same time at night, the moon progresses this night, next night, next night, next. The same with the sun, that gradually goes through the ecliptic relative to the fixed stars this way, the selection sphere this way. But things that can get into opposition, basically we can approach and outrun. So it's like parallax. You see things relative to the background. So there's an apparent motion that it looks like it's going forward, and then all of a sudden looks like it's going back. It's because we're basically outdistancing it, so retrograde. And exhibit retrograde motion. Okay, maybe while we're at it, it's a good picture. Here's a picture. I don't know if you can really see it. Here is the sun. Here is the Earth on the inside track and Mars on the outside. And Mars coming up on the outside. The Earth is going through. So Mars is basically going this way through the sky, but then the Earth's coming on the inside track and passing Mars, so it looks like it's going backwards, and then after a while it keeps going straight. Okay, so that basically you look at the apparent motion against the stars, and it looks like it's going forward, and then it looks like going backward, and then forward. All right. What's the geocentric view versus the heliocentric?
Geocentric is the belief that the Earth is the center of the solar system.
Earth is the center. So geocentric, Earth is center, and heliocentric is sun. What are the differences? Well, obviously the center is different. How about the orbit order and the geocentric? What's the first object that is orbiting? Let's just take a look there, because we didn't talk about that yet. Here we have Earth at the center, the geocentric view. Maybe I'll make this bigger.
They thought everything circled us.
Yep. Maybe. Okay, so Earth is the center. Obviously we are, because everything is moving, we're sitting here. That's the obvious view. We're not moving, everything else is moving. It's all going around us. Every night we see stuff going around us. The stars go around us every night. And the same with the day. The sun goes around us, the moon goes around us, stuff like that, but then night by night it goes around us from a slightly different place. So the sun and the the moon and the planets seem to be wandering against the heavens, which seem to be going at slightly different rates. So the thing that's going around the fastest pretty much is the moon. Put that there first. Then Mercury seems to be going around, but basically we have orbits, but then we have orbits within orbits, or circles within circles, epicycles, and all that kind of stuff. Call it deference, the deferent, which is basically the cycle here, and then a epicycle is there. Very complicated motion, but that actually could account very well for motions of Mercury and Venus, and retrograde motions of the superior planets. We have the moon, Mercury, Venus, the sun, then Mars, Jupiter, Saturn. So it starts with moon, Mercury, Venus, sun, then the planets, superior planets, Jupiter, Saturn. That's it. And we know the progression here, Mercury, Venus, then the Earth and Moon as a pair, then Mars, Jupiter, Saturn, and so on.
Does that mean that other planets' moons don't orbit around the sun?
Yeah, the heliocentric view says the sun is the center, and all of these orbit the sun. And it was Copernicus that said that they orbit in circles, perfect circles. But that didn't match up well. In fact, it didn't match up as well as Ptolemy's view. Okay, so who are the proponents? Proponents of the geocentric. Who are the proponents of the geocentric versus the heliocentric? People didn't read. Aristotle, good. Aristotle for the geocentric. Who else? Aristotle. Another one, the other main one was Plato also, but Ptolemy was a big one because he had this very detailed mathematical model. And his mathematical model produced the data very well. So that's a necessary condition of a good mathematical model, is it reproduces data. However, it was, in spite of it being a seemingly very good model in reproducing the data, it was completely wrong. So you can reproduce data and still be completely wrong. But that's a necessary condition. Sufficient condition has to match up with all the other phenomena, and it helps to be simple and elegant, which Ptolemy's model definitely wasn't very complicated. Heliocentric, who were the proponents there? The first one. Well, okay, we could say the first one. Huh? Copernicus in the modern era, but maybe in Aristotle's more the old era, Aristarchus, then Copernicus, and then Galileo, and those are the key. They put the nails in, basically Copernicus and Galileo, and I would say Kepler probably there. Put the nails in the coffin of the geocentric model. All right. What is the declination of the equator?
0.
Good. 0 degrees. So the equator is basically 0, just like our equator is 0. A declination corresponds to latitude. So 0 degrees. Good. How about the zenith?
90?
It's a good guess. I mean, 90 degrees away from declination is kind of like the zenith in the equatorial coordinate system. But we say zenith is straight overhead. So 90 degrees corresponds actually in the equatorial system to what? We have 0 at the equator, 90 points which way? People don't know their cardinal points here. Which way is that?
North?
North. Okay, that's the north celestial pole. So 90 plus 90 is north celestial pole, minus 90 is south celestial pole. Zenith is basically, you take the equator and everything, here's the zenith at the equator. The equator is a 0 declination up there, but you keep going north in latitude, then everything tilts. So everything tilts down 38 degrees, and basically 38 degrees from here, 38 degrees from the equator, is the zenith. So wherever you are in latitude, so it's 38 right now, here. So the latitude is the declination, your zenith has a declination of your latitude, just like the North Star has the altitude of your latitude. Okay. Let's see, at what altitude does the equator transit the celestial meridian? You talked about it, you might have forgotten. Celestial meridian, remember, north, zenith, south, and then the equator goes from east, up, down to the west. And if we tilt down, going north 38 degrees away from 90, that's where the equator is maximum, that's where it transits the celestial meridian. And that is 38 below 90 is what?
52.
Yeah, that's it. So 52 degrees altitude. Zero degrees declination, but in the altitude azimuth way of looking at things, it's 52 degrees above the horizon. Of course, that's just due south. Due east is at 0 degrees. Same due west, just right goes down at the horizon. All right. How about the distance in parsecs for a star with 0.50 arc seconds? Did anybody get an idea what that was? I think I've mentioned it.
Would it be 2 parsecs?
That's exactly right. So the distance in parsecs is equal to 1 over the number of arc seconds, say that, parallax in arc seconds. So half an arc second means 2 parsecs. And in light years, that would be how much? Parsec is 3.26 light years, so 2 of those, about what, 6.5 or so light years. About 6.5. So we got 1 over 0.5 equals 2 parsecs, which is about 6.5 light years. Okay, the star moves 30 degrees across the sky. How long have you been watching?
About 2 hours.
That's right. It moves about 15 degrees per hour. In 24 hours, it moves 360 degrees. So that's 15 degrees per hour. So that means 30 degrees in 2 hours. Okay, good. Okay, any questions on these things? Okay, we're starting to get deeper into chapter 2. We should. So we already talked about the geocentric universe, the heliocentric model. We said, I think already, that the church, the Catholic Church backed Aristotle. And when Aristotle was found out, then people threw out the baby with the bathwater. Said, oh, religion can't be any good. It's got to be science. So people choose science over religion for truth all the time. It's too bad. Because there's different types of truth for different types. There's the material universe. There's there's emotional well-being, spiritual well-being, all these other things, there's different kind of things. So there are laws for both. Religion, philosophy studies the laws for the internal, and we look at the external through the eyes of science. It used to be the geocentric view, but then, despite Ptolemy's ideas to make something look very, should be simple, everything orbiting around the Earth because of retrograde motion and the subtleties of motion of planets and their cycles in epicycles and all these things to account for that retrograde or the various types of motion. But in any case, it produced a basic view that the inferior planets, they were inside the sun, in this case. Venus, Mercury, Moon basically stayed, these things seem to stay pretty close to the sun. Of course, the Moon went around independently. And the Mars and Jupiter, Saturn could be opposite the sun in principle. In principle, Mercury and Venus could be, but the way Ptolemy worked it, didn't have to be. But it seems kind of unreasonable because it's so complicated. But it satisfied people for a couple thousand years. It's not bad. I mean, if some show is running a couple of thousand years and people are still going to it, that's a pretty successful show. All right. Copernican revolution. It wasn't the first time. We said Aristarchus originally had the idea, we published the idea that the sun was the center, not the Earth. But Copernicus came along just about the right time. It was right after, let's see if I have it. Yeah. So he came along right about the time of the Protestant Reformation. Protestant Reformation, Martin Luther banged his 95 theses on the wall, the wall, I forget, it was Göttingen or it was a major
The
church.
story's apocryphal, but
I don't know what's apocryphal. But basically, he put his 95 theses on a major church in Germany. That was the beginning of a protest against all the stuff that the Catholic Church was into. And so people started to think more freely, started to reason things a little bit more, not just accept dogma. And so Copernicus came along and said, no, the dogma of the church may be that the Earth is the center, but it doesn't make sense to me. So he said we can have a much simpler view and explain the retrograde motion without resorting to epicycles and all that. So he put the sun at the center, and the Earth is just one of the planets. All planets revolve around the sun. Stars are very much farther away than the sun. And parent movement of stars is due to the Earth's rotation. Parent movement of the sun is also due to the Earth's rotation. Retrograde motion is this apparent motion due to the Earth relative to the planets. And then all other things orbit the sun. Let's see, all other planets orbit the sun. But his circles didn't quite match up as well as Ptolemy's ideas. He was afraid to publish, so he let it be published on his deathbed because they brought you in and made you toe the line. Maybe they would chastise you, and then if you didn't submit then maybe they show you some instruments that they were going to torture you with. And then if that didn't convince you, then maybe they'll torture you. But convince most people. Convince Galileo, I don't know if he was actually shown the instruments, probably. You're called on the carpet, right? and then you show them the instruments. They put Galileo in house arrest for agreeing with all this stuff. So that was a big problem. But Galileo did, and he used the telescope, which he didn't invent, but he used it after his invention, to show people certain things. Most importantly for people was Venus has phases that do not correspond with a geocentric model. That convinced people. There are a whole bunch of other things. Jupiter has moons as well as us. We're not unique. The moon has mountains and valleys like us. We're not unique. Sun is not perfect and pristine, has sunspots or blemishes, it also rotates. So there's a lot of things he was able to see. And here's the idea of the geocentric versus heliocentric phases. If Venus does go around an epicycle like this, then its back basically is always pretty much to Earth, and you can never see it with a bright disk like you can here. Maybe a couple of weeks ago, I was at Yellow Valley College. We were setting up telescopes for basically working out, not the bugs, but just getting an idea how to work some new telescopes. And the things we viewed during the day were the moon. You often see the moon. We also saw Jupiter. We also saw Venus. And when you saw, you got to be a little careful. I mean, when you start to look close to the sun, then it gets really bright. So you got to be really careful. But if you have it well, how should I say, aligned with the stars, you press Venus, it'll just go right to Venus. And it was a super bright. I mean, it was super bright disk. And it was not, maybe it was over here, and it corresponded to one of those. And the only way you can get that is if Venus is orbiting the sun, not the Earth. The epicycle. Okay. So the telescope, this happens a lot in science. New technology begets new understanding. The understanding is then compared to the current view, and you ask, does it match or not? If it doesn't match the current view, a lot of people might want to throw out or shoot the messenger or shoot the data, get rid of the data, keep the current view if they have a vested interest. That happens all the time in science. Scientists are human beings. They're not just governed. They're often not governed by the desire for truth. Often they're governed by the desire for a job, for research grants, for fame and fortune, like anybody else. So that's what happened. I think that's what's happening a lot in some of today's science. But it happens everywhere, whether it's government money or it's, corporate money or whatever. Anyway. Now, let's see. Back to Copernicus, one of the fundamental things about the Copernican idea is that the Earth is not special. We are not special. The Catholic Church would want people to think, well, we're the center of God's idea and providence, and therefore we are special. And in the internal sense, that may be true. If you're a believer in religion, that very well may be true. If you're not, that's neither here nor there. But Copernicus basically decoupled the physical from the internal and said the external, the physical, isn't like that. We are just one of the planets, nothing special. One of the planets going around the sun, like all the other planets. We have moons, and other planets have moons. We have mountains and valleys, other things. The moon has mountains and valleys. And that kind of idea is used really to how should I say, to make, as a filter for to guide our inferences for science ever since. So, for example, especially astronomy ever since. So, Hubble, I don't think we'll study him in this course, but Hubble found that there was more than the Milky Way galaxy. Furthermore, all the galaxies are moving away from us. Looks like we're the center. If everything's moving away from us, we must be the center. But the Copernican idea says no. We can't be unique. So if we can't be unique, then you have to think, well, what does that mean? If there's no center, then you have to think, well, everybody thinks they're the center. If you take a balloon and put dots on it, every place on that balloon, as you blow it up, will look away. If you look away from that dot, all the stars, the galaxies will be moving away from each dot because the whole space is expanding. So this led him to the idea of expanding space. It was about the same time that, or a little bit later than Einstein came up with his idea of space and time and gravity and these kinds of things. So therefore, we're not a unique place. I would extend that to, people think people who believe in aliens are crazy. But that's ridiculous. From a Copernican point, it is inevitable. It is the only conclusion. We're not unique. Therefore, there must be alien life. Where? Everywhere. Who knows how dense the populations are. But the Copernican view would be, yes, of course there are. The question is, have they gotten to us? Have we interacted? Have we really seen? And we don't even know, according to Einstein, there's a hyperdimensional kind of space. There could be other dimensions. Alien life could come from, or other intelligent life could come from, and pass through here. All sorts of things. There's all sorts of stuff you can think of if you believe in the Copernican idea. And that's been very powerful and very successful so far. After Copernicus came Galileo. After Galileo was Newton. Just about the time, I think it was almost maybe the month, I don't know if the day, that Galileo passed and Newton was born. Kepler came in around the time of Galileo. Then there was also fellows by the name of Fermat and Barrow that were contemporaries of Newton. All of these gentlemen work led to a deeper understanding of nature. In particular, Kepler's laws. Kepler came along and he had a mentor, or benefactor maybe, who was very wealthy, Tycho Brahe, who built an observatory where he could take data. I guess if you were very rich at that time and you don't have TV, there's not a lot of things going on in town. So but if you're interested in astronomy, you can take a lot of time doing that. So he made lots and lots of observations of the planets and stars, very detailed and very precise. Kepler used those to show that the orbits, I think it was first Mars, were not circular. Mars' orbit turned out to be elliptical, a little oblong. Then Mercury's orbit and other orbits, he found that they all had certain relationships with one another. First of all, elliptical orbits. The ellipse, kind of oblong shape. These X's denote what are called foci. And basically, if you take a string and put it around, say, two pins at the foci, and put a pencil out here and then you keep it taut, then you will draw a focus by keeping it taut all the way around. You'll draw an ellipse by keeping it taut all the way around. So the ellipse is we say locus of all points whose sum of distances from these foci are constant. And he said they're elliptical orbits. The sun is at one of the foci. And how should I say it? A qualitative way of saying his second law is that the closer you get in this ellipse to the sun, then the faster you go. The farther you get, then the slower you go. It's called equal areas and equal time. Basically, the distance times the speed is a constant. And then 3, he found that the periods of motion, one period is a year for the Earth, the periods of motion were related. And in particular, he found the periods in years, let's see if I get this right, squared is equal to the semi-major axis. I'll tell you, well, okay, I'll do that. It's Q in astronomical units. The semi-major axis, this whole thing has a width of twice the semi-major axis. The semi-major axis would just be that. Okay. So basically the Earth is almost circular in orbit, that's 1 AU. If you cube 1 AU, you get 1 in AU, you get 1 in a year, okay? 1 squared in a year. If you look at Jupiter is about 5 AU. So what would be the period for the Jupiter in this case? 5 cubed is equal to something squared in years. What would that be? What squared would equal roughly 5 cubed? What is 5 cubed? How much?
5 times 5 times.
100, yeah, it's 125
125.
times 5, 25 times 5, 125. So it's about 125 in AU cubed. Or just say, yeah, just say. And then the period squared is that, so what would the period be in years then? Yeah, about 11. 10 would be a little bit too small, 12 is too big, 11 is almost just right, it's 121, so the period would be about 11 years.
Didn't they just send like a drone over to?
Say again?
Didn't they send a drone over to Jupiter to like investigate it?
Yeah.
Oh, they-
spacecraft.
That's it.
Yeah, they sent a number of things toward Jupiter, Voyager, Galileo, a number of. Let's see. Okay, so these are the 3 laws. Then Newton came along, and he showed why these laws were true. Laws of motion, law of gravity. Now, the laws of motion, you've heard maybe F equals ma. A is acceleration, m is mass, F is force. And one of the fundamental forces is the force of gravity. So the force of gravity is, okay, I'll just write it out. Is a constant, g, the universal gravitational constant, times the mass of one object times the mass of another object divided by the distance between them squared. So you might have something like this. And there's a law of attraction. And in fact, there's something we call gravitational acceleration, which causes things to fall all at the same rate. Galileo found that. Everything fell about the same rate, and got faster at about 10 meters per second each second. So you have big ball, small ball, you drop them, they'll fall at the same rate. And they'll drop 10 meters in the first second, but then, I shouldn't say that. They'll drop to go from 0 to 10 meters per second in the first second, and the second they'll get to 20 meters per second and 30 meters per second and so on. And he also found a rule for how distances vary with a square of the time. Okay. Let's see, what else should I say? Okay, so these laws, basically, you can show that if you have a circular motion of Earth, for example, or say some object, say some planet P, goes around roughly at speed v, and the speed v is the distance over time. And the distance all around, what do we call once around? What do we call that, once around a circle?
Circumference.
Yeah, circumference. There's a diameter, there's a radius, there's circumference. So the distance is actually 2 pi times the r. And the time is the period we call, for Earth, what would be the time of one cycle?
24 hours.
That's one cycle of rotation.
365.
But for orbit, it's 365 days. So that's the
Okay.
kind of cycle we're talking about, the orbit around the sun. So it would be, one cycle, or just say the period. And then Kepler had his, the period in years according to the semi-major axis, all that stuff. And R is related to 2 pi r would be related to that semi-major axis, all that stuff. And so if you know we say the semi-major axis, which is related to R, in AU, and you know the period in time that you know from Kepler's law, then you can show that if the sun has a certain mass, then the mass of the sun is v squared times r over g, turns out. This is Newton's prediction. So if you're in physics 2A or 8A, then we would do this, we work from the first principles and derive that.
Are we gonna have to do any of this math in this system?
Could, yep, a little bit, could be. Yep. For example, parallax, you might be asked something like that. You'd probably be asked if you double the, another thing, the velocity of the orbit. This, maybe I'll show, let's see, where should I put it? Maybe I'll put it velocity of the orbit is square root of, let's see, G-M sun over R. So if you double the size of the orbit, this is the mass of the sun, then, or if you quadruple the size of the orbit, you would cut this into 1/2. Or if you have, or say, cut this into 1/4, then you're going to double the speed of the orbit. This is basically an orbital speed. If you had a star that was twice the mass, then at the Earth's radius, or distance, I should say, the orbital radius, then the speed would be higher by that square root of double, square root of 2, about 40% faster to keep an orbit around that star. If you, now, so let's just say this, let's put this as an exercise here. Where are we, 8 or 7 maybe, 7?
7.
7. Say, if you double the mass of a body and double the radius, how much more, less would you weigh? Now, that doesn't make sense, that question, unless you realize weight is the force of gravity on you. So basically, I'm asking how much the force is there if you double the mass of a body, say they have a gravitating body, and also doubles the radius. What will the force be? So let's take that and see what happens. Of course, you're the same mass. So the gravitational force would be G M, and that's the M of U over R squared, my mass. How much more would you weigh? Your mass. Okay, what do we got? Anybody want to take a stab at it? 4? That's a good guess, definitely. Any other ideas? 4 will stand. Let's think if you double the mass of a body. So we'll say there's a new force. I'll just call it new. And we got the same G, but we're going to do double the M. Got the same little m, and we got double the radius. Okay. So if we do that, we got a factor 2 up here. We got G big N little m, and we got 4 in the denominator, and we got R squared, and so that's equal to 1/2 our original force. That was our original force. So if we double the mass and double the radius, then definitely you're going to have some factor 4 in there. 2 squared in the denominator and some factor 2 up here, so you got to lunge them the right way. That's all. Yes?
The radius of what?
The radius of the object you're sitting on. Say, for example, we sit on the Earth, for example, right? At a certain radius. Here we are with some mass. There's a mass of the Earth, and it's some radius. So we have some distance from the Earth's center. So if you took not the Earth, but some any old thing with a certain mass, and has a certain radius, double its radius, double its mass, then what force are you going to feel? Just use Newton's law, and that's what that is. So you should be able to say, well, if you double the mass of something, then you're going to have twice the force. If you double the radius of something, you're going to have 1/4 the force. You should be able to know that, say that. Okay. Now, when Newton understood his laws of motion, laws of gravity. And then also there was, Fermat and Newton's boss, basically, Isaac Barrow. Then Newton and a fellow by the name of Leibniz put together, sort of compiled and unified and gave good notation, at least Leibniz did, a very good notation to a new branch of mathematics called calculus. Calculus is how you figure out ratios of things and rates. And Newton was one of has been known as the inventor of calculus, but it's much more complicated story than that. Newton didn't have the key, in fact. It was his boss that had the key. But Newton put it together and he solved some very fundamental problems of astronomy using it, and therefore he became famous for it. In fact, there was another fellow at the time, a fellow by the name of Hooke, had the same idea of the distance of the force being inversely proportional to the distance squared between objects. But he didn't get the credit for it because he didn't solve some fundamental problems in astronomy. Newton did, so he got the credit instead. But there was a big controversy about who gets credit for this or that. That's always the case. So, I think we'll be surprised in some future time if we're able to see the details by some universal way of accumulating all the truth. What is the truth of what really